So I'm considered one of the one of the technical directors for Element, and considered an expert in vibe shock, obviously, in seismic, right? So that's why we're here. All right, explosive atmosphere. The reason why we run it is inside the aircraft, or you can get buildup of fuel vapors, and if your unit turns on and off or does something, we want to make sure it doesn't explode the environment. All right. So we demonstrate the ability of the material, your test item, to operate in a fuel air induced without causing ignition. So it's pretty simple why we run the test. The first thing we'll do is this is one of our explosive atmosphere chamber. This happens to be up in Massachusetts. The one in Plano looks pretty much exactly the same, just a little bit smaller in length. So the way the chamber works is obviously we have the door where we you load your equipment in. We have a feed-through port. If you have a lot of cables, you're going to have to work with us so we can get. So leakage is a problem. Obviously, we're going to 40,000 feet, so we got to make sure everything's sealed in the chamber. During the test, we do leak it down at a certain rate, but if your cables have shields or anything, you need to cut those shields because that's usually where the biggest leakage comes through. We got articulated arms, so you can flip switches in there or whatever you may have to do to get the unit working. Around the outside of the unit, it's jacketed. We use peanut oil up north. We heat the chamber. That's why the chamber is convection into the unit, so the chamber has to be within 6 degrees of the unit. It used to be 11 degrees, right, in the older standards. That's how we heat it. And then off to the side here, we have a test chamber. I call it a Poppet chamber. So once we do everything inside the chamber, obviously we'll go through the test procedure. We'll pull off a sample and we'll spark it and make sure it pops. So in our chamber, this plastic cover just pops up when it explodes. In the chamber here in Plano, they're going to have a bung that pops out. So either way, so that way we can tell we get a good test. If it doesn't pop, then we have to restart all over again. All right. So.
The red, is that a viewing port?
Yes, that's a viewing port. Yep. Yep. All right. So this is directions from MIL-STD-810. All right. So when do we run the test? You get a sequence. You run into MIL-STD-810. You do it at the beginning, the end. This approach tells you should probably do it pretty close to the beginning. I'll tell you right now, 99% of the customers run it at the end, just to make sure. If you think you got a problem, you probably should run it at the beginning because you got a big redesign coming. But more than likely, we'll run it at the end, along with the contamination tests. Sand and dust and fungus. We mentioned fungus, right? Fluid contamination. So all those tests we sort of lump at the end. So the limitation is we use Hexane. The spec does allow you to use other fuels, whatever fuel you may want to use. And Hexane's a little bit more volatile. The standard sort of says you can use anything you want, but you should use Hexane. So we're using Hexane. The method doesn't simulate suspended dust or heavy aerosols inside the area. So if you have a storage facility or whatever way you get suspended dust, that is not what this test is intended for. Testing is restricted below altitudes of 52,000 feet. We can't prove atmosphere. We tried one at 60,000, and it's very hard to prove that we get ignition. There's very low oxygen, so most of the time we're running at about 40,000 feet. It seems to be the standard. So there's a limitation there. And the test specifies target spark ignitions from relays, switches. Back in the day, when you had relays, open relays, and things like that, we had a lot of failures. Nowadays, very few and far between failure. But I'm telling you, if your unit fails, you'll know it. You won't be asking us. Yeah. So it's it gets pretty loud. Yeah. So I should have pointed that out. The top of the chamber has a vent, so if we do get an explosion, everything vents up. And heck, I think it expands to 50 times when we get an explosion, somewhere in that neighborhood. So inside the document, there's two procedures. Procedure one is the one we've been basically talking about, where we put your unit inside the chamber and we manipulate it. And as we drift down, you're going to continue to operate, and we make sure we don't explode the environment. Procedure two is for units that are designed to contain the explosion. So we'll put our own spark gap inside your unit. We'll set the environment the same way, and then we'll suck it inside your unit, seal it off, and then we'll pop the inside of the unit and make sure it doesn't set the rest of the chamber on. So I think we do that 25 times. So that's a unit that contains the explosion, so we do make it explode. And then we got the units that are outside that are pretty standard. P2 is pretty rare. We do run it. A lot of labs don't run it. But Element, I think 2 or 3 of us will do a P2. Because you need a spark gap, you need to seal it. It takes a little bit of work. So, all right, and hexane. So this is the fuel we were talking about using. It's considered a hazardous material. If you can't get exposure for more than 8 hours to it and a few other things. So part of our safety thing, I just have to let you know when you're out in the chamber if we're using in hexane. We use 95% with 5% other hexane isomers. Ignition properties is higher. The optimum hexane will ignite at temperatures as low as 220 degrees C. So it's stable, but not really stable. So the minimum ignition energy for hexane in the air is 0.29. So spark energy. So use for other fuels other than hexane is not recommended, but you can use it if you want. If you want to use whatever, JP4, JP, Jet A, Jet A1, whatever, it is allowed. And then our little safety video. So it's a hazardous material warning. It's listed as a hazardous material. So exposure to it is limited to time. As you can see, it's class 3, but just so you're aware, when we're filling the chamber and doing things like that, we usually get the customers out of the room. All right. So there's a certain mixture we use inside a chamber to make it volatile. There's a formula in and this is something we all calculate. So it's the chamber volume, the chamber pressure, which is 40,000 feet or ambient, the temperature we're at, and the specific gravity in hexane. There's a chart in MIL-STD-810 based on the temperature that hexane tells us specific gravity. So once we run through this formula, depending on the altitude we're at and the temperature we're running the test at, it could be 50 C or 70 C or whatever temperature you want. We'll calculate how much in hexane we have to dump into the chamber by weight. So they'll be out there. We'll do some calculations and we'll make some measurements, and then we'll take the hexane and inject it into the chamber. And then we have a fan inside the chamber that mixes it up. So in one of our examples, so this is the chamber you saw. So in this test, we were running the chamber at 50 degrees C. The fuel temperature was 25 degrees C. Was room temperature for our specific gravity. So the specific gravity came in at 0.65. Anyways, you go through all the math. We're going to put in 60.47 milliliters into the chamber. So your unit gets in there, we get it to altitude, we get it to temperature, make sure it's within a certain temperature of the wall. Then we'll inject this in hexane at 40,000 feet, or 2,000 meters above 40,000 feet. And let it mix, and then we'll run through the test. So one thing you got to pay attention to, though, is So you're going to start at 40,000 feet. You're going to do 2,000 meters above, 2,000 meters below, and then sort of drift down to ambient. When we drift down to ambient, we're going to add in some more fuel once we get to 2,000 meters above fuel, because now the mixture changed and the pressure in the chamber has changed. Right? So we're adding more fuel. So the calculation ends up being 328 milliliters, but you got to subtract the amount we already put in the chamber, because that fuel stays in the chamber, right? Hopefully it stays in the chamber. So when we remix the fuel and re-add it at ambient, we'll do the calculation and subtract how much we already put into the chamber. Okay. Any questions yet? So this is something the technician will do, elements technician will do. All right, test temperature. So what do we test to? You have a high operating temperature, method 502, that's high temp, right? So whatever you run high operating temperature at on your unit, that method, that's going to be the temperature that we're going to run the test at. The highest anticipated operating altitude, it's usually 40,000 feet. Most tests run to 40,000 feet, but if you're on a helicopter or something different, you're going to 12,000 or 15,000 feet, whatever it may be. So it is adjustable. Unless permanently sealed items for maintenance purposes, we're going to remove or loosen external covers. So we're going to make sure that air-fuel mixture gets inside your unit on covers that it used to be you undid and redid the covers 10 times, I think, and then you put the cover back on. Now we just take the covers off. So anything inside the unit gets exposed to our air-fuel mixture. All right. And then we're going to pop it at 40,000 feet, and then we're going to pop it at ambient temperature, ambient pressure as well, while maintaining the temperature. It's usually 50 C. Most operating temperatures are around 50 C. All right, so we're going to install the unit like we talked about. We're going to verify the unit operates, obviously feed throughs, and then we're going to seal up the whole chamber. Once we seal the chamber, we're going to stabilize the test item in the chamber air temperature to high operating temperature for a minimum duration of 1 hour. So once we'll have a thermocouple on your unit, once the unit reaches within 5 or 6 degrees of the wall temperature, or we'll wait 1 hour, make sure that the temperature gets inside the unit, thermally stabilized. If you have a larger system, we might wait 2 to 3 or 4 hours to make sure everything thermally stabilizes, but most of the time an hour works and the temperature can permeate. We'll adjust the chamber air pressure to 40,000 feet plus 2,000 meters. We'll start 2,000 meters above 40,000 feet, with 14,200 meters. I don't do metric, but so I'm sorry if I'm going back and forth between units. But so we're going to slowly introduce the volume in hexane we calculated into the chamber. We're going to begin reducing the simulated altitude at a rate of no faster than 100 meters per minute. So what we do is introduce a little leak in our chamber. So you're sitting at 14,000 meters. We'll slowly start drifting down to your test altitude and drift through that for another 2,000 meters. The whole time you're going to be operating your unit. Whatever you need to do to operate the unit, flip switches, run traffic. If it's steady state, that's fine. And the whole time we'll be monitoring it, make sure the unit runs fine. We're going to continue circulating the atmosphere to reduce the chamber. At 1,000 meters above the test altitude, verify the potential explosion of the fuel air mixture. So what we'll do is at 1,000 meters, we'll draw off a sample and we'll pop it in our chamber. All right, and hopefully it pops. It should pop if we did everything right. We use a spark gap. Some people use glow plugs, so we use a spark gap so you can actually hear it and see it in the Poppet chamber, or the test chamber. If ignition does not occur, purge the chamber and the fuel air mixture, and you're going to start all over again. All right, so it usually doesn't happen too much, so we're usually pretty good. All right, although the maximum operating altitude of the test item attempt to operate the unit, because remember we're 2,000 meters above your max operating altitude. So continue to operate the unit as we ramp down. We're going to pop it again and then verify the potential explosion. All right. And instead of going through all the steps, it's easier if I just skip through some of these. All right, so this is actually what we do, okay? And it's nice and visual and easy, right? Instead of going through all the steps. So we'll bring your chamber up to test altitude, add in hexane. We'll slowly start drifting down while you unit, and then we'll draw off a sample and make sure it works, okay? And then we'll again, 100 meters per minute, we'll draw off our sample and make sure it works. We'll re-add in hexane at 2,000 meters above site pressure, drift down, and then drift down, pop it, and pop it. And the whole time your unit's operating. This test, depending on your operability, can go in a day. Sometimes it could take a couple of days, depending on how much operability you need to do and things like that. You can see the whole time we're holding max temperature, and then you can see where you need to power up the unit. While we're drifting down between, you can obviously power down the unit if you want to. A lot of people just leave it up and running. All right, P2. So this is the one where you'll give us a unit. Unfortunately, we need to drill holes in your unit. It's just the way it is. We got to get our spark gap in there. We need a way to draw the fuel in. So we'll hook lines up, run it outside the chamber, and we'll make sure that the atmosphere gets inside your unit. Once it's inside the unit, and we run the test the exact same way we've been running it, we'll seal off your unit, and then we'll set off the spark gap. We'll explode inside your unit, and what we're looking for is to make sure that doesn't spread to the outside of the unit, okay? And most of the time we're doing this 25 times, so we stress the chassis. And that's basically what we do. So the same thing is forced air items and cool items. You need to prop for items not using forced air, drill and tap the case to insert a hose and other things in the outlet hose, just like we talked about. You do not change the internal volume by more than 5%. So we want to make sure that our spark gap doesn't take up a lot of the volume to make sure we get enough fuel air mixture in there. So sometimes that can be a problem on these smaller units. Something we'll work with you guys on up front if you need to do a P2. Ensure the points of ignition are not more than 1.2 centimeters from any vent or hole. So our spark gap, we need to be close to a vent or a hole, especially if you have airflow. I mean, it can be a problem. You know, you need suppressors and everything on your outlet air and all of that. I'm trying to remember if I ever did a P2 with airflow through the unit and actually passed. I don't think so, but it's in the spec if you want to do it that way. Usually it's totally sealed off from the environment. And then ensure that the air is within the test chamber within 10 degrees C. So again, we heat the walls and then we convection into your unit. So we got to make sure your unit's within so many temperatures of the wall. So, all right, so we place the item, the model, the test item with the same volume and configuration within the case, and install the case inside the explosion chamber, as we talked about. We seal the chamber with the test items inside and raise the temperature, same thing we did in P1. When the temperature of both the unit and the test item within 11 degrees of the chamber, we reduce the chamber air pressure to 200 meters above, and so you can see we're going to repeat this whole cycle over and over again. The only difference, instead of drawing it off, we'll actually set it off and make sure it contains it inside the unit. So yeah, I mean, same thing. Introduce the quantity of hexane. That doesn't change. It's the same volume. Slowly decrease the simulated chamber. Pull the sample and make sure it pops. Make sure it explodes. Energize the internal case ignition source and confirm the occurrence of explosion within. So we need to confirm that our spark gap actually worked. So we can do it with temperature. We can do it a few other ways. Usually we do it with temperature. So we need to confirm that we had explosive atmosphere inside your unit, and that did go off, and so that didn't set off our chamber. So we'll have thermocouples in there usually to let us know that the unit did, we did get an explosion inside your unit. So.